SwayamPrabha. Digital India. Educated India.
Hello. In this video, we will be looking at the generalized Maxwell and Kelvin models. We need to recall that the Kelvin and Maxwell models we discussed are now the building blocks for us to develop these generalized Maxwell and Kelvin models, because these generalized Maxwell and Kelvin model are actually which can be used to model a real polymer, because in a real polymer it has several relaxation times or the retardation times which cannot be captured by a simple one Maxwell model or a one Kelvin model. So, we will start by looking at two Maxwells in parallel. So, we will develop the stress strain relations and then we will also solve for the relaxation response. Using that as a basis, we will then move on to the generalized Maxwell model, which we can use to find the relaxation response. And finally, we will be looking at the generalized Kelvin model and look at its creep response. So, let us start with the two Maxwells in parallel. So, we have this Maxwell 1 with modulus E1 and viscosity nu1, and similarly the other Maxwell model with E2 and mu2. So, for this, first let us look at the equilibrium equations and the kinematic equation. So, since these, so here the subscript 1 represents, we are talking about the first Maxwell model, and the subscript 2 represents the second Maxwell model. Since these two are in parallel, the stress is a sum of the stresses in the first and the second Maxwells, whereas the strain is same. So, the total strain epsilon is equal to the strain in the first Maxwell and is equal to the strain in the second Maxwell. Now, let us look at the constitutive equations of each of these Maxwell models. So, first we will look at the first Maxwell model, where we represent this sigma 1 as the stress in the first Maxwell and epsilon 1 is the strain in the first Maxwell. So, here we have represented the stress strain relations that we have already derived in previous videos. So, earlier we mentioned that D is the differential operator, and we also said that it follows the rules of algebra. Okay. So, we will be using that is the reason why I am emphasizing. Now, let us look at the constitutive equation for the second Maxwell model, which is similar. The only difference is now we replace the stresses with sigma 2 and strain with epsilon 2. Okay. So, now that we have the constitutive equations of the first and the second Maxwell model, let us see how we can use this information to develop the stress strain relation for these two Maxwells in parallel. So, for that let us number these equations, let us say 1 and 2. So, from 1 we should be able to bring this stress term sigma 1 and move the other coefficients to the right hand side. So, this should be mu d epsilon 1 divided by 1 plus. Now, I will replace this mu 1 by E1, which is nothing but the retardation time or the relaxation time. So, we will represent it with tau 1, where tau 1 is simply mu 1 by E1 times d, fine. And from equation 2, where we now replace tau 2 as the relaxation time given by mu 2 by E2, then I should be able to write this stress sigma 2 as mu d epsilon 2 divided by 1 plus tau 2 times d. Okay. So, these are the extensions to these constitutive equations 1 and 2. So, now what I will do is we will invoke these equations, let us again number these equations as 3 and 4. So, looking at this kinematic equation, we know we can replace this strain in the Maxwell elements with the overall strain epsilon. So, which means this sigma 1 can now be written as mu d epsilon by 1 plus tau 1 d, and sigma 2 can be written as mu d epsilon by 1 plus tau 2 d. This we have written by invoking this equation 4, but now coming back to equation 3. Now we should be able to write the overall stress is simply the summation of sigma 1 and sigma 2, which are mu d epsilon by 1 plus tau 1 d plus, okay, I need to mention that this is mu 1. Even in the equation here it is missing, so let us write it, okay, and mu 2 times d epsilon divided by 1 plus tau 2 d. So, this we need to do a little rearrangement so that we can send these d's to the stresses. So, it will be 1 plus tau 1 times d times 1 plus tau 2 d times the stress equals 1 plus tau 2 d times mu 1 d epsilon plus 1 plus tau 1 d times mu 2 d epsilon. So, once we have this equation, we just need to operate this d over the sigma. So, we will see that there will be d terms and d square terms, meaning the first derivative and the second derivative. So, let us first write this equation and then we will simplify it further. So, if you are looking for only sigma terms, you will have only sigma plus, now we are, if you are only looking at the d terms, it will be nu 1 plus nu 2 times d sigma, which is nothing but the stress rate or sigma dot plus tau 1 tau 2 times d square sigma equals. Now let us look at the first, are there any strain terms? No, it starts with the first derivative of the strain rate. So, let us write that as mu 1 plus mu 2 times d epsilon plus the second derivatives are tau 2 mu 1 plus tau 1 mu 2 times d square epsilon. So, once we replace these d epsilon with sigma dot, d square sigma with epsilon, sigma double dot, and then these with first derivative of the strain and the second derivative of the strain, what we get is this final equation in the standard form. So, in this final form what we have done is we have replaced these d sigma with sigma dot, d square sigma with sigma double dot, d epsilon with epsilon dot, and d square epsilon with epsilon double dot, and this is in the standard form. Because to the left hand side we have the stress terms and to the right hand side we have the strain terms, and these each of these terms are in the increasing order of derivatives. So, we start with sigma first derivative of stress and the second derivative of stress. To the right hand side we have the first derivative of strain and the second derivative of strain. But overall what we have seen is we have shown you an approach by which one should be able to develop this differential equation for a two Maxwells in parallel. But one thing to notice is the differential equation is not simple anymore the way we have seen for a Maxwell model or a Kelvin model, because now we are also looking at the second derivatives of stress and the second derivative of strain, which was absent earlier when we were only looking at Maxwell or Kelvin. So, which means solving these equations become even harder because of the more complex differential equations we are having with. So, we need to find ways to solve these problems for at least the basic loads like creep and relaxation, that we will see in the next slide. So, we said we are again looking at these two Maxwells in parallel, but this time we will be interested to know what is the response to relaxation load. So, as we all know, relaxation load is given by this sigma naught times the step function h of t. And since both of them are in parallel, we said the equilibrium equation is stress can be written as sum of stresses in first and the second Maxwell model. For the first Maxwell model, we can find the stress response as sigma 1 of t, which is the stress in the first Maxwell, is given as epsilon naught E1 times e power minus t by tau 1, where tau 1 is the first relaxation time given as mu 1 by E1. Similarly, for the second Maxwell, the response is given in terms of sigma 2 stresses in the second Maxwell in terms of E2 and tau 2, where again here tau 2 is the relaxation time for the second Maxwell given by mu 2 by E2. Okay. Now that we have the stress response for each of these Maxwells, then finally it is very easy to find the stresses for these two Maxwells in parallel, because we just need to sum these two together. So, with that we get the stress response is simply the stress in the first Maxwell plus the stress in the second Maxwell. But since we are looking at the relaxation response, usually we represent it with relaxation modulus. So, how can we write the relaxation modulus for this? It is simply E of t is given as sigma t by epsilon naught, which is the load, and with this we get it is simply E1 times e power minus t by tau 1 plus E2 times e power minus t by tau 2. So, what we have seen is we are able to find the relaxation response in terms of these two relaxation times tau 1 and tau 2. But previously we said for a real polymer we need many more relaxation times. So, how can we get those relaxation times? By increasing the number of Maxwells in parallel. That is what we will now see, and which we now call it as the generalized Maxwell model, meaning that you have the first Maxwell with E1 mu 1, second with E2 mu 2, and so on we have until n, En mu n. So, for this so earlier we mentioned that this n will be usually a large number if you are trying to replicate a real polymer, sometimes in the range of 5 to 15. Now, let us look at the relaxation response. Earlier we only had two terms because we only had two Maxwells in parallel, but now if we extend this to n in parallel, we have n terms given as the last term is En times e power minus t by tau n, where tau n here is the nth relaxation time given by mu n by En. So, noticing this, we see that it will be easy for us to write it in a summation form, and once we have in a summation forms, we use this variable I going from 1 to n, and these terms can be simply written as ei times e power t by tau I. Again, tau I here is mu I by E I, viscosity by modulus. From this stress response, we should be able to write the relaxation modulus given as E of t times the summation. We simply remove this epsilon naught because E of t is simply sigma t by epsilon naught. Okay. So, now let us try to get some physical meaning of how this responds. For that, let us for this stress response, let us see what happens at time t equals to 0. So, e power 0 is 1, which means this will be simply epsilon naught times summation of I is equal to 1 to n E I, or in other words, it will be the sum of all the spring modulus E1 plus E2 so on up to En times the strain applied epsilon naught. So, and then this is all instantaneous stress we get because of the relaxation load applied. But now let us see what happens as we wait for a very long time, meaning that t tends to infinity. When t tends to infinity, this e power minus infinity is 0, so it reaches 0, the stress value reaches 0. Usually this is the way it can be represented is, let us see. So, if one is plotting these in a log scale, meaning the changes in the relaxation modulus E with time, these steps are the relaxation times at which the modulus changes, and this should be approaching to 0. So, approaching to 0 is good for representing a thermoplastic, but let us say if we want to represent a thermoset where it does not go to 0, how do we modify this Maxwell model? For that, we just need to add one more parallel element, but this time it will be only a spring without a damper. This final expression for the relaxation modulus is very important, and this also has a name called as the Prony series. So, usually when this is very commonly used in the commercial finite element software to model the viscoelastic behavior. So, ideally you need to simply provide what are these values of Ei and tau I. So, depending on value of n, if it is 5, if n is equal to 5, basically you need to provide E1, E2 till E5, and then the relaxation times tau 1, tau 2 until 5. So, once you provide this table, these act as the material parameters which are required to model the particular material as a generalized Maxwell model. So, this is very important, especially in the implementation of these viscoelastic models in commercial finite element software. This is the Richet model where we have an extra spring in parallel. This extra spring makes sure that when you apply a relaxation load, there is an instantaneous response, or the stress increases suddenly, but given longer times the other dampers relax and go to 0 stresses, but this last one without represented as E infinity, this stress remains constant, meaning that even if you wait for long times, the response is a non-zero modulus. So, at time t tends to infinity, we get a non-zero value for the relaxation modulus. But now let us see how we can write the relaxation response. So, we will use the earlier expression which we named it as the Prony series, and to that we will add this extra term E infinity, because this is the instantaneous instantaneous stress coming from the last element, which is a single spring in parallel. So, for this now let us see what happens at sigma at t equals 0. T equals 0 is simply epsilon naught times E1 plus E2 plus so on up till En plus E infinity. And when time t tends to infinity, this should go to epsilon naught times E infinity, because the rest of these exponential terms go to 0, but the free, it is not the free spring, but the spring which is in parallel will still contribute, giving as epsilon naught times E infinity. So, and this is good to model the thermocells, and the earlier generalized Maxwell model is good to model the thermoplastics. So, once we have seen this Maxwell model, now it will be easy for us to discuss about this Kelvin model, because now instead of having these Maxwells in parallel, we will have Kelvins in series. So, this is Kelvin 1 with E1 mu 1, and then we have the second Kelvin with E2 mu 2, and so on and so forth till En mu 1. So, the nth Kelvin model. Like in early case, we can now add a free spring in series, that we call it as the generalized void Kelvin model. So, because now we have this free spring, which we will represent as E naught, and the rest are this normal E1 mu 1, E2 mu 2 and En mu 1. So, let us look at the creep response, meaning that if you apply a instantaneous stress, what is the strain with time, how the strain changes with time. Again, looking at the equilibrium equation and the kinematic equation, one should be able to write the strain. Strain is simply the summation of strains in each of these elements. So, then we should be able to write this first term is coming from the free spring, the second term is the first Kelvin model, this is the second Kelvin model, and this the last term is the nth Kelvin model. So, this long equation can now be written in terms of summation, where in terms of I going from 1 to n, in terms of this Ei and tau I, again this tau I is the relaxation time or the retardation time given as mu I by Ei. From the strain response, we should be able to write the creep compliance given as d of t. We simply need to remove this sigma naught, and then we have this first term from this free spring and the rest coming from each of the Kelvin models. So, one can even add one more element, meaning the free damper to this, and when we apply the free damper, now we call it as the generalized void Kelvin solid with a free damper. So, what we are introducing is this mu naught or the free damper. So, we can use the earlier expression by simply adding the extra term. This is the viscous flow term. This previously we said is the instantaneous elastic term, and this is the delayed elastic term. So, if you look closely, this is very close to our 4 parameter model. The only difference between being in the 4 parameter model we only had 1 Kelvin in series, here we have n Kelvins in series. So, that is the reason why we have this final expression looking very similar to the creep response of a 4 parameter model. So, finally, to summarize, we started with 2 Maxwells in parallel, where we are able to derive the stress strain relations, but we noted that we get a very long or a complicated differential equation, which is difficult to solve even for simple loads. For that reason, we said for finding the response we will use the superpositions. We started by looking at the relaxation response for a 2 Maxwell models. Using the same approach we extended it to generalized Maxwell model and where we found the relaxation response. And finally, similar to the Maxwell model, we also have a generalized Kelvin model where we have all Kelvins in series. And here is the creep compliance given by d of t. So, with this we conclude by our discussion about the phenomenological models, where we started with Maxwell and Kelvin model, later we moved on to the 3 and 4 parameter models, and in this video we discussed the generalized Maxwell and Kelvin models. As a final point, we usually use this generalized and Maxwell model to represent a real polymer, because with this it is possible to bring in multiple relaxation times or the retardation times, which a usual polymer shows. So, in the next week we will be looking at the stress analysis of the polymers. Until then, bye.